All right, the floor is yours.
Okay, so yeah, thank you for this kind introduction, and of course also for the invitation. So I give a bit of an introduction to dark matter, and then I talk, of course, about direct detection, and in particular about xenon. So I hope those in xenon will not get too bored. So it's very early, well, not very early, but it's early here and it's blue skies. But if it would be dark, and if you were to look at the sky in a dark, clear night somewhere here in the mountains, of course, what you would see is, and well, what you would see is this beautiful band, of the Milky Way. But we also know here that you would actually be marveling at a minority of matter in the universe. And we are, of course, part of the Milky Way, and together with the solar system, we move with around 220 kilometers per second around the galactic center. But if we could look at the Milky Way from the outside, it would look very much like Andromeda, which is our closest large neighbor, about 2 million uh, light years ago. Now, very briefly on the history of dark matter, because Fritz Zwicky, he was a Swiss-American astronomer and actually the first one to make a compelling case. Not the first one to mention dark matter, but maybe to make a compelling case for the existence of this invisible matter. And as I'm sure you all know, he was able to measure the radial velocities of galaxies in this very large, very rich cluster of galaxies with more than 1,000 galaxies. And what he could see that these velocity dispersions were way too large, right? So he postulated that there wasn't enough gravitational attraction from the stars and gas within galaxies. And back then, actually, this hot intracluster gas was not even known yet. But there wasn't enough matter to keep these galaxies from flying apart. And he published this in 1933 in Helvetica Physica Acta. Um, the article was called Die Rotverschiebung von extragalaktischen Nebeln. And here, he wrote that should this hold true, it would mean that dark matter is present in much larger amounts than luminous matter, right? So he called it dunkle Materie. Now, you probably also know that he was not an easy person to get along with. So there's this nice book, Fritz Zwicky, Astrophysiker, Genie mit Ecken und Kanten. There's also a translation. So he remained true to his nature as a native of Glarus, not so far from Zurich, actually, as a mountaineer. And he also was inclined to provocation, right, to put it mildly. But of course, his ideas were quite unconventional and time and again brilliant. So I'm citing from this book. And you also know that he worked on supernova explosions, on neutron stars, and so on. So it was much later, as we also know, that Vera Rubin and Ford and others, they observed similar effects in the behavior of spiral galaxies. So they didn't see this expected Keplerian decrease in the orbital speeds of stars and gas as you move out from this galactic center. And, Vera Rubin said back then, she said that in a spiral galaxy, the ratio of dark to light matter is about a factor of 10. That's probably a good number for the ratio of our ignorance to knowledge. We're out of kindergarten, but only in about third grade. So yeah, maybe now we are in sixth grade or so. We shall see. Okay, so that much about the history. There's much more, of course, but fast forwarding uh, almost 100 years, actually. The evidence for dark matter is there across many time and length scales in the universe, right? From early and late cosmology to, well, clusters of galaxies. Of course, now we have very different ways to measure the total mass of clusters, to galactic rotation curves, BBN, and so on. Also, we have this so-called standard model of cosmology, right? The lambda CDM that describes all observations quite well, right? It's the simplest explanation. There's only a small problem. at least if we talk here about cold dark matter, namely that the fundamental nature of dark matter is still a mystery. So this is what we are about, what we are after, right? So what is the dark matter? How does it interact? What are its quantum numbers, assuming, of course, that it's a new particle? So just on one slide, what do we know about dark matter? Exists today in the early universe. We have quite a lot of constraints from astrophysics and more are coming, and from searches for new particles. No color charge, no electric charge, no strong self-interaction, slow moving, right? Non-relativistic as large structures formed. So when we say no color charge, no electric charge, and so on, it always means as far as we can measure today, right? It also must be stable or very long-lived. So if it's not stable, then its lifetime must be larger, of course, than the age of our universe. So we know that it's cold or perhaps warmish. That's not yet excluded. Warmish meaning, as we will see, KV scale dark matter. So this is an undergraduate textbook that probably many of you know, by Barbara Ryden, cosmology textbook, and she said a component of the universe that is totally invisible is an open invitation to speculation. So in terms of what the dark matter could be, there's about 80 orders of magnitude in mass that it can span, but for now we come back to that. So that's obviously a much higher number for the ratio of our ignorance to knowledge than what we had seen from Vera Rubin. But for now, this is all of the known physics, right? This roughly 5% of the total matter and energy density, and no particle of the standard model is a good dark matter candidate. That's probably also clear. Now we have all these candidates here spanning about 80 orders of magnitude in mass. There's also many orders of magnitude in cross sections, as we will see, all the way from what is called wave-like dark matter. So axion-like particles, for example, 10 to the minus 22 electron volts, and the constraints on the mass come from the fact that the Broglie has to be such that structures on the scale of dwarf galaxies are still allowed to form. We have here the QCD axion, then what is called light dark matter from some dark sector that is only very weakly coupled to the luminous, to the standard model sector. The WIM paradigm, it's not yet dead. I would say it's still alive. We're still looking, as you will see, for weak scale dark matter, then composite dark matter, and all the way to primordial black holes with a few tens or so of solar masses. So we are searching with the experiments that I will talk about for quite a large range of candidates. But we cannot do everything with the same kind of experiments. So here I'll focus mostly on this light and weak scale dark matter. So how to see in the dark, in our case at least. So on the one hand side, we are looking for collisions of dark matter particles, via some mediators with standard model states, and the standard model states could be electrons of the atoms in our detector materials in the atomic shell, or traditionally, of course, we have been and are still looking for scatters of dark matter particles with atomic nuclei. Right, and we will talk here about talking about experiments, we will discuss about so-called electronic recoils, so when dark matter particles scatter of electrons, and nuclear recoils when they scatter of nuclei. I'm not going to show much here about this, but just to say that we also look for absorption of light bosons via either the axioelectric effect or via their coupling, the dark photons via their kinetic mixing with the standard model photon, for example. And this is where we can probe KV scale dark matter particles. So yes, we are moving, as we mentioned, together with our sun around the galactic center. We imagine these particles as being some sort of non-interacting kind of ideal gas that make this, extended halos of galaxies and also of the Milky Way. And when we move, we feel this dark matter wind coming onto us, and roughly, the scattering rates will be proportional to the number of targets of scattering centers, either electron, nuclei, the number density of these particles that's proportional to the local dark matter density and the mass, and then some convolution between the velocity of the dark matter particles and the scattering cross-section, okay? And because of this motion we will see that we also expect, because of the motion of the sun, of the Earth around the sun, and also because of the rotation of the Earth around this axis, we will expect also some temporal variations in the rates. Now, I like to say that this is a very interdisciplinary field, because to be able to predict what we can see in a detector, for these event rates, we really need inputs from several fields. On the one hand side, of course, from particle physics, ideally, we'd like to know the mass of the particle and its scattering cross-section. But this is something that we constrain because, we do not know. We have only constraints on cross-sections, basically from having not seen particles so far. From the astrophysics, we'd like to know, on the one hand side, what's the local density, but it is a linear factor that enters the predictions, and there's still quite, some uncertainties there, but roughly the local density is about 0.3, 0.4 GeV per cubic centimeter. So what does it mean? If you have a 100 GeV particle, that would mean that the flux is about 10 to the 5 particles per square centimeters per second on Earth, right? Now, maybe those of you who are doing neutrino physics know that this is a very small flux, right? So, for example, PP neutrinos, the flux that we measure here on Earth is 65 billions per square centimeter and per second. The velocity distribution is quite important, especially for the high velocity tail. So usually we assume this Maxwellian distribution, and there could be some modification to it. And finally, because we are scattering in the very low, in the very non-relativistic limit, these particles are moving, with about 10 to the minus 3 C. We also need to deal with atomic and/or nuclear physics form factors. And there are many theory groups, nuclear theory groups, who are working on calculating these form factors for all kinds of interactions. Now, just about the kinematics, this is a nice figure from Tony-Yang Lee's study lecture. So we have here the deposited energy, the mass of the dark matter particle, and this is the kinetic energy, right, of this particle. So if you are talking about nuclear recoils, even on very light nuclei, such as helium, then you can see here for a GeV scale dark matter mass, the deposited energy here, is electron volt keV, right? So it's quite small, right? It can go up to a few tens of keV or so. So for electronic recoils, of course, because electrons are so much lighter, in terms of the kinematics, you can probe also lighter dark matter masses. And as you can see here, right, so you can go to, below MeV up to keV scale. And in terms of technology also, you can probe light dark matter masses when you employ phonon-based detectors, because it takes, kind of milli-electron volt to create phonon excitations rather than electron volt or so for other kinds of excitations in your material. And you will also see that we haven't seen any conclusive evidence, I would say, for a dark matter particle yet. So I will show you this kind of exclusion plots and just one slide for you to understand. So what we show here is usually the mass of the dark matter particle as a function of the interaction cross-section, and these curves will go up at low masses because at some, because of the energy threshold in your detector, at some point, the nuclear recoil energy, for example, will be so low that it's below what you can actually see in the detector. Then you will have some maximum sensitivity here. And then finally, if you go to higher mass dark matter particles, then the sensitivity is not zero, but it will go with 1 over the mass of the your dark matter candidate. And this is because we have seen that the rate depends on the number density, right? That's the local density divided by the mass, okay? So you will see this kind of plots. And quite some time ago, I calculated here the interaction rate. So roughly speaking, you will expect about 0.1 events per kilogram of your detector material per year, modulo the atomic mass number, the cross-section, that's a cross-section here that has been long excluded by now, the mean velocity and the local density. So you can see here this different. Now this is the total rate, but here what I'm showing is the differential rate as a function of recoil energy for scalar type of interactions, what we also call spin independent. For a given wind mass and a cross section, you have here xenon, germanium, argon, silicon, and so on. So these are materials that are used in direct detection experiments, and because xenon is a heavy nucleus, you have a higher rate, but because of the nuclear form factor, and that rate declines, earlier than for lighter nuclei here. And this is one relatively recent calculation for the so-called structure functions for a nucleus here of xenon that has a non-zero angular momentum, where you can also probe axial vector coupling, so spin-dependent interactions. And these you, of course, need to take into account when you compute the equivalent rates for spin-dependent interactions. Okay, so what are now the main experimental challenges before we come to actual experiments? So we want to observe a signal that is very small in terms of the energy deposit. So low recoil energies, electron volt to keV, we don't know, perhaps even milli-electron volt, right? Depends on the mass of the particle, very rare. Based on the fact that we haven't seen yet these particles, roughly about below 1 event per kilogram year, as you will see at low masses, or below 1 event per ton in year at higher masses. And as always, when you look for very rare interactions, the signal is probably hidden in backgrounds that are millions of times higher than what you're looking for. And it has been a challenge, and it still is, to reduce these backgrounds, over the years. So you have to go deep underground to suppress backgrounds coming from cosmic rays and basically muons, right? Muons are 206 times heavier than electrons, so they can penetrate deep underground. And you reduce the flux, by a factor of 1 million or maybe 10 millions, but it's still not enough. So you also, as we will see, you have to surround your detector by so-called muon VTOS, neutron VTOS, and so on. And apart from going deep underground, you also have to reduce the radioactivity of your detector materials to very, very low levels. So typically, we talk about specific activities of microbecquerel or so per kilogram. But okay, so yes, so we do, this is just an example here of the muon flux that I mentioned as a function of depth. And because of the density of the rocks is different for different underground laboratories, these are rescaled in terms of kilometer of water equivalent. So I work here at the Gran Sasso lab in Italy that has these three big experimental halls. And the muon rate there is reduced by a factor of million compared to the Earth's surface. So it's about 1 per square meter and hour. But of course, there are much deeper labs like Snow Lab in Canada and the Jinping in China. That's the deepest underground lab, where you really don't worry much about the muon background. However, no matter how deep you go, you can't shield neutrinos, right? So this is a good thing and a bad thing. The bad thing is that, yeah, you can't shield them. Eventually, they will become your ultimate background for your dark matter detector. But on the bright side, you can look for signals from a variety of astrophysical sources, and we'll come to that later in the talk. And this is so for many years we were talking about the neutrino floor and that means like it's a hard boundary, a floor, you just crash down on it, and that's not really what's happening. That's why some people started to call it the neutrino fog, because it's soft, right? It's a soft boundary, and we will, softly dive into it, as we will see. This is a nice paper by Ciara O'Hare from 2021. So this fog, of course, is different. Okay, maybe I should explain what it is. So this is the region here where neutrinos from different sources will come backgrounds. And let's for dark matter detectors, okay? So you have here the solar neutrinos, so 7 beryllium, boron 8, and then the atmospheric neutrinos, and there's also the diffuse supernova neutrino background. And there's some uncertainty because these fluxes, especially the atmospheric neutrino flux, there's maybe 20% or so uncertainty just by the fact that it has never been measured at these low energies that are relevant for us. Okay. Yeah, we'll come back to this a bit later, but the neutrino fog is now defined as the region where the experiments leave the Poissonian regime, meaning where the dark matter discovery limit will scale as 1 over the n root of the what we call exposure. This is just the mass times time of your experiment. Just one thing, because you will ask me, well, if you shield all of the backgrounds and so on, how can you be sure that if you see some particles above your background, it will be from dark matter? And it will be very hard, of course, to make a compelling case, but we do have some signatures. I showed you how the rate depends on the target material, but it also depends on the mass. So for lighter dark matter, you have a much steeper recoil spectrum than for heavier dark matter particles. That means also to be able to see that you need low energy threshold. And then finally, the motion of the Earth causes, on the one hand side, this annual event rate modulation between June and September. It's a large effect, but a lot of things can unfortunately modulate with 1 year. And a larger effect that's on the one hand, on the other side, harder to measure is the sidereal directional modulation. Because with most of the detectors, we cannot actually measure the direction of this nuclear recoil, right? But there's R&D in this direction. So this is just a very broad overview. Probably I missed some experiments here of the techniques that are used to measure this, either so-called nuclear recoils or electronic recoils, right? So on the one hand side, heat or phonons. We have these cryogenic dark matter detectors that are operated at a few tens of millikelvins. Then we have scintillation light and ionization. And many of these experiments can measure, 2 of these observables, because the ratio will allow you, as we will see in the case of xenon, will allow you to distinguish at least between these nuclear and electronic recoils, and thus do what we call particle discrimination. Okay, so we have experiments that measure phonons and either phonon and charge, like, for example, Super CDMS, Edelweiss, or phonon and light, like CREST, and a new cosinus experiment. Then we have experiment looking for scintillation light and charge, like the large liquid xenon-based detectors. And finally, some of them, looking for charge, and and heat. I already mentioned this. I'm not going to talk about this here, but there's also a new broad range of experiments that are so-called quantum-based, that use quantum-based sensors to probe even much lighter dark matter particles. And this is kind of a new field. So this is a plot from last year. I will show you some update, but just to show you very roughly where we are. So yes, at this low, so this is about here, this 10 GeV. So at low masses, there's still quite some parameter space at these higher cross sections that can be explored. And this is mainly with with cryogenic detectors, but also with these new technologies. And then when you go to larger masses, above roughly 10 GeV, up to all the way up to 100 TeV or so, you need, of course, experiments that have ultra low backgrounds that you can also scale up, right, to tens and tens of tons of masses. And more or less, there's this still factor of 10 or a bit more to probe until we will reach this boundary that I will show you a concrete example actually for the neutrino coherent scattering from atmospheric neutrinos. Now this looks like a small sliver, but also because the Y range here is pretty large, right? So when I started, since you mentioned Heidelberg, when we started with the Heidelberg dark matter search in 1999, 1998, we were around here, right? So there was quite a lot of progress in terms of, well, not finding the dark matter particles, but also excluding, this large parameter space. So this is a plot made by Tina in Amsterdam, and I like it because it shows, it's a bit busy, so I will try to explain it, but it shows roughly where we want to go. So on the one hand side, we are looking for electronic recoils, and we want to go below the background that comes from neutrinos for electronic recoils. I didn't mention this yet, but it's a neutrino electron scattering, for example, also from the sun, mostly from the PP neutrinos, right? So we want to decrease this radioactivity from detector materials. Again, I'll show you a concrete example later, below this ultimate background that will come from PP7 beryllium neutrinos. Now, for the WIMP, which gives us this nuclear recoil, we want to reduce this neutron background that also fast neutrons also induce nuclear recoils to below the background that comes on the one hand side here, and we already managed that, as I will see, that comes from the boron 8 neutrinos, and here from atmospheric and diffuse supernova neutrino background. So these neutrinos scatter with nuclei via so-called coherent elastic neutrino nucleoscatter. This is a process that has been predicted, decades ago, but only recently been observed for the first time by coherent and now also by other experiments. So I'm coming to, let's see how much time I have, maybe 15 minutes.
Well, at least 20 minutes, 30 minutes. Yeah.
Oh, okay, 20 minutes. Oh, great. Okay, good. Thank you. Yes, so I'm coming to the detectors that we have been using over the past decades, namely liquid xenon time projection chambers. I call them 5D detectors because we measure the position, the 3D position, the energy, and the time of a given interaction. So we have a large volume of liquid xenon, and we have a gas phase, the vapor phase on top that's in thermodynamic equilibrium with the liquid phase that we keep everything around 2 bar, and we have a photosensor array, one that's immersed in the liquid and one that is placed above the liquid. And we also apply an electric drift field. So what happens is that when a particle scatters in the dense liquid, you create a so-called prompt scintillation light signal. We call this signal S1. So this is scintillation in the VUV, vacuum ultraviolet region, 175 nanometers. So the energy is about 7 electron volts of these photons. And to measure, to observe these photons, you need special kind of photosensors that have these quartz windows so that are transparent to this VUV light. Okay? Now, in an interaction, you also create a few free electrons, and by virtue of this field, you drift them upwards, and you apply here between the gate and anode higher. So the drift field is typically 100 volts per centimeter or lower, but you also apply a higher so-called extraction field so that these electrons overcome the potential barrier between the liquid and the gas. So they're extracted into the gas phase where they collide with xenon gas atoms and create what we call proportional scintillation light signal or electroluminescence. And that's an amplified, this is a way, so this signal is linear to the energy that was deposited in the first place in your detector. Yeah, it's amplified, it's a larger signal that we call S2. Now, from the time difference between S1 and S2, we get the Z position of an interaction in the detector. From the light pattern that we observe in this top photosensor array, we get the XY. So from the light distribution, we get the XY position because this S2 signal is very localized. There's no much lateral diffusion of the electrons as they drift upwards. From the two signals, we also get, we can also reconstruct the total energy with quite nice resolution. That's, that's important for dark matter search, but even more important for other searches that I will mention. And finally, by looking at the ratio of the two signals, we can also discriminate between these electronic recoils and nuclear recoils. Okay. So what are the existing large liquids? So there's a long history here. At least in xenon, we started with a small, with xenon 10, xenon 100, xenon 1 ton. I'm going to skip all of that history. And we are now xenon N-ton. So there are three large liquid xenon experiments that use these time projection chambers in the world. So it's the Lux Zeppelin at SURF in South Dakota with 10 tons of liquid xenon in total. We have xenon N-ton in Gran Sasso, and I will mention it in somewhat more detail with about 9 tons of liquid xenon in total. And then in China, in Jinping, there's the Panda X4 ton with 6 tons of liquid xenon in total. And all of these experiments use the same type of photosensors, 3-inch VUV sensitive PMTs. They also use krypton and radon removal techniques, ultra pure water shields, neutron and muon VTOS, and so on. I'm mentioning krypton and radon because, as we will see, as you reduce the radioactivity of your detector materials to sufficiently, let's say, low levels, you need to get rid of other noble gases that mix with your liquid and then can decay and give you backgrounds like 85 krypton and 222 radon. So these have to be removed via, for example, cryogenic distillation techniques. Now, this is the xenon N-ton experiment in Gran Sasso. So we have the service building that's 10 by 10 meters, about 10 meters high. We have all of the cryogenics up here. We have the radon distillation column. We have the data acquisition room. And then we have here the storage system for the xenon and also krypton distillation column. And then you can see here a large water tank that would be pretty boring. So we have this picture that's glued on top of it, where you can see what's inside. So the muon VTO, the neutron VTO, the cryostat, it's a double-walled stainless steel cryostat, the nice support structure, and the TPC inside. So why do we need? Let's see if I have a picture. Yeah, that's a nicer picture of the neutron VTO. And of the detector. So basically, we have 3 nested detectors, and we need the muon VTO to reject any events where you have a coincident muon going through, and then leaving some energy also in the TPC. But we also need this neutron VTO that's just around the cryostat, because sometimes neutrons, which are emitted by materials, they don't come from muons. We call these radiogenic neutrons, so they come from alpha N reactions and fission reactions. They would scatter only once via nuclear recoil in your detector and then get out, right? So it could look like a WIMP scatter if you don't have multiple interactions. But once they get out, we have here this gadolinium doped water Cherenkov detector, so similarly to Super Kamiokande. And then these neutrons after a few microseconds, captured on gadolinium. So you have a cascade of high energy 8 MeV gammas that you can then detect with these arrays here of photosensors. Yes, and then finally the DPC inside. At least in Zurich, we were mostly working on the TPC. What you can see here are these field shaping rings. This is to ensure a uniform drift field across the TPC. You can also see the two photosensor arrays in these two hexagonal patterns. So you have to find some optimum arrangement that basically you optimize your total light collection, and you also optimize for the top PMT array, you optimize the position reconstruction. Yeah, maybe I'm not allowed to show this. I'm not totally sure if it's blessed, but we had several science runs in Xenon. So we had the SR0, as we call it, the first. Then we had sorry, where's my mouse? Yeah, then we had the second science run, and then we also had the third one. But what I'm showing this is, this is the accumulated, what we call exposure over time, already more than 550 days. But so far, we are showing results from these first two runs. And then we are analyzing the data also now from the third and the longer run. I'm also showing this because apart from taking what we call science data, you also have to make sure to calibrate your detector. To understand its behavior, to define what is the signal, what are the background regions, to measure the light and the charge yield, and also to look at the stability in time, but also in position. So that's why we have all kinds of calibration runs. Okay, so I'm not going to go into the details. And I'm
Sorry,
already,
sorry,
yes,
Laura. What were the
yes.
colored lines, the different elements, the colored lines that you had? What are
Right.
the?
Okay. So, right. So there are different calibration sources.
Mhm.
And some calibration sources, like for example, that's an isomer state of krypton 83 that we inject into the TPC and we mix it with a xenon. This has two low energy lines from X-rays and Auger electrons at about 9 and 34 kV. So here we measure the stability of these detector parameters over time, but also in space. So to also define like spatial and temporal corrections. Then we use radon 220. That's also something that you can inject in your TPC to map what is this electronic recoil band. I'll show you a bit later how it looks like. So to define what is the either signal region for electronic recoils or background region when you look for nuclear recoils. We also then we take calibrations with neutron sources that, however, we don't mix with a TPC. So they are deployed in, around the cryostat. And these are, for example, an americium beryllium source. There is an yttrium beryllium source where we took a calibration with much lower energy neutrons. You will see later why. Argon 37, we do usually at the end of the run because of its long half-life, 35 days. But we do this because it has an X-ray at low energies, basically 2.3 kV, to look at the performance, if you want, of the TPC at these low energies, and so on. So sorry, this was
Okay,
the neutron
thanks.
source here, the yttrium beryllium, exactly. And now I should say we also deployed a neutron generator, the diffusion generator that's pulsed. So now we are also taking. We have just finished a run with this neutron generator that allows us to define even better the so-called nuclear recoil energy region. So this you already see data from our latest paper. Well, I have it in the next slide. So first of all, this is the so-called electronic recoil band. Now for a second science run, we divided this into two sub runs, not so important here. But this is, yeah, the electronic recoil, this is where we would expect here, this is a contour where we would expect a 200 GeV WIMP, right? And these were events that we saw in this region after the unblinding. So we have several background populations. We have events that happen, and we classify these, of course, with calibration, with sidebands, and so on. We have events that happen close to the surface of the TPC. We have the so-called accidental coincident background that's most relevant at low nuclear recoil energy. So that comes from accidental pairing of an S1 and an S2 event that are, however, not correlated by an actual physical interaction, and so on. So we had an earlier publication last year where we could set constraints for light dark matter. So between here, as you can see, about 4 GeV up to about 12 GeV mass. And you can see that we are approaching here the so-called neutrino fog. And I'll come back to that a bit later. And recently, just last week, so this plot is actually from this recent paper. We submitted for publication new constraints on this medium to heavy dark matter, right? So yeah, 10 GeV up to here, 10 1 TeV and also above. So as you can see here, this is our new XenonnT constraint. This is the LZ from 2023, and we also have here Panda X 2025. So it's something that I didn't mention, but for these nuclear recoils, we have, at least at this stage, a somewhat lower sensitivity than our competitors because we have a lower drift field. We did not achieve our desired drift field, so our discrimination between these nuclear recoils and electronic recoils is not as high as we wanted it to be. Okay. On the other hand, as I will show you, we did achieve the lowest background in a dark matter detector for these electronic recoils. But before we come to that, just a few slides on a future Xeno. Yeah.
Sorry, could you say something about those 2200 GeV 2 sigma contours in the previous paper?
Mm-hmm. Yes, sorry.
Yeah,
so these are right. I mean,
right.
so we show this contour as an example here. We also have similar contours. So I'm not sure. So what is the actual question?
Events. So there's
no events. There are
Okay.
events, but the probability that they come from WIMPs is very small, let's say. So we have some events, but they mostly come either from some leakage of this electronic recoil band. So yes, or from from other backgrounds, but not really from WIMPs. But yeah, if you would have now you can see this curve goes a bit up here, so we will see what happens, right? So this is what we call here the Brazilian plot with our sensitivity bands, and this is here the actual limit that is above here, this median sensitivity. Yeah, exactly.
Thank you.
So just a few slides in terms of future detectors. As you have seen, Xenon, LZ, we keep taking data, the same for Panda X. We have been doing R&D in Darwin for, well, more than a decade now already. And a few years ago, we decided to join forces together with our competitors in LZ. So we call this new collaboration XLZD. We have a design book that's been out now for a few months. So the idea is to build a detector where we have 75 to 80 in total, 60 tons in the active target, and also within the baseline design of these 3-inch PMTs. There's quite a lot of R&D and prototyping in progress. I will show some of it, and also several underground labs are under consideration. On the other hand, Panda X, they are planning for the Panda X X-ton detector that will have a total of 47 tons of liquid xenon, 43 in the active target, and they already decided for different kinds of PMTs that we are actually also studying these 2-inch flat panel PMTs. But as an intermediate step, they are building a 20-ton detector. And LZD, we are also considering an early stage with about 45 tons of liquid xenon. So when you see this TPC here, I mentioned that the current one about one. This is 3 meters larger than what we have been constructing so far. So yes, size matters. This is actually a nice picture that my colleagues in Amsterdam made. This is just to show what I just said, right? That this next generation detector will have a much larger diameter and height. So that while we think we have, between these two large collaborations, the detectors look similar, but if you look at the details, they're quite different. So we think we have the knowledge on how to construct this next generation detector. But of course, there are quite some technological challenges. And to address these, we also have large demonstrators. And since Daniel mentioned grant, in our case, we built this vertical demonstrator xenoscope where we have a TPC that has a 2.6 meter. This was the original size of a tall TPC. Kilograms. In Freiburg, my colleagues built a so-called pancake. That's a flat but very wide TPC in order to test, for instance, these very large, at least for our scales, very large electrodes, right? So there's quite a challenge on how to build them to be robust, but also transparent, low electron emission, and all of that. And so there are many, many small challenges, but another big challenge is also, and you will see this why in the next slides, is also to reduce the radon that is constantly being emanated by detector materials. Even if you go to microbecquerel, or now let's say millibecquerel per kilogram of uranium and thorium, radon is part of the uranium chain and is being constantly emanated. So it mixes with a xenon, and then it has what we call a naked beta decay of 214 lead. So that doesn't come with any gammas or anything that you could tag, and that gives us background from this beta in the low energy region. So that's why my colleague Christian Weinheimer in Münster, he also has an ERC advanced grant to build this a demonstrator to reduce the radon content such that the background for this next generation detector is factor 10 below the solar neutrino rate. Okay, so that's a goal, factor of 10 below the rate that comes from solar neutrino. Just some pictures in my lab last year, long TPC. We had from a purity monitor in the previous year, and now in March, actually, we are planning to start a new run. So we plan to demonstrate that you can drift very few electrons over this distance, and we also want to measure the longitudinal diffusion and the transversal diffusion of the cloud as you move. There are predictions, but they have to be. And then a few other measurements. Coming back to XL, we were a consortium for a few years now, and last fall we moved to a collaboration. We also have a siting committee, and we have 3 main sites that are being considered. This is Gran Sasso, a new lab at Baudis, and SURF. Some of us are working on the Gran Sasso option, and you see here, this is the larger hole C, where Borexino is being moved out. So there Legend 1000 that's already been approved to be built in Gran Sasso, dark side 20K. So this is a 50-ton liquid argon dark matter experiment. And then XLZD would be here in the middle. So this would be the 12-meter Cherenkov water shield, what you see here in blue, the storage systems, and the service building. But yes, not yet been decided. This is a, maybe we can come later, but basically it shows these contours when, for a given contour, a 10 times increase in the cross-section sensitivity requires an exposure of, 10 to the n. So if n is 2, you have 100 times higher exposure. But you can see this is where more or less LZ is now, and this is where we'd like to go with XZD. So maybe the main message to take here is that you really need very large exposures, so 1,000 ton years to dive in this atmospheric neutrino fog, right? So here you start to see one event, then 10 events, and so on. And of course, this fog will move if we if we get a better handle on the systematic uncertainties coming from this neutrino flux. But of course, the ideal case for WIMP, so 20 GeV contour. And these are also some theoretical predictions here from an electroweak multiplet dark matter, for example, from this paper from Bottaro and others. Okay. Just a historical plot that I need to. When I started, we were using high purity germanium crystals for dark matter searches, then bolometers, and of course, bolometers are still used. This is here constraints evolved over time for a 50 GeV mass, okay? And this is where we want to go. And at some point, this liquid XenonnT TPC started to pick up. And yeah, I have to update this plot with a 2025 value, but this is eventually, we want to go down. And this is a logarithmic plot, right? So it took, well, about 40 years or so. Obviously before I started, but to get to these really low cross sections. And yes, why I'm so excited? Obviously, I'm excited to keep looking for dark matter, but I'm also excited that with this, actually with the current generation of detectors, but also with the future, XLZD, Panda X, Xton, and so on, we can do a lot more. Our main goals are to detect solar neutrinos, so the PP neutrinos, to measure the flux and the rate at these very low energies, then also the boron 8 neutrinos, nuclear scattering. One of our big goals is to look for neutrinoless double beta decay with 136 xenon. That's present at about 9%. That's abundant. Yeah, the abundance is 9% in natural xenon, and also, of course, supernova neutrinos. So we are already now part of SNEWS with xenon nton of this supernova neutrino, network. And just one example with xenon 1 ton, that was a much smaller detector. Some time ago in 2019, we saw for the first time this extremely rare nuclear decay, right? So this is the 2 neutrino electron capture xenon. We made it to the cover of Nature, not because this is new physics, of course, right? So it's a standard model process where the 2 from this, from the double electron capture process, so KK shell, KL, and so on. But it was the longest half-life ever measured directly. And for us, it was great because it showed that we have this very, very high, very low background, very high sensitivity. I should say that now, these lines are background, of course. I mean, they give you some intrinsic calibration lines, but on the other hand, we are also doing these line searches that I didn't mention in this talk, ALPS capture and dark photons. And for these kind of searches, this is now obviously background. But another search, I'll come back to that later, but another search that we are doing is this solar neutrino to measure the PP flux at low energies. And this was our background in science, in the first science run. And here, you know, what comes from materials, what comes from this radon here of xenon, the 2 neutrino, 136 xenon, and so radon level in our back then, that was 1.8 microbecquerel per kilogram. The solar neutrino was already half of this main background component. And here I will only say that in the following run, this radon background was reduced, you know, from about 1.8 to 0.8 microbecquerel per kilogram. That actually allows us to do this search. And on the other hand, another search that we've been doing was to look for this coherent.
Sorry, Laura.
Yes.
Maybe 5 more minutes or
5 more minutes. Yes, that's okay. Yeah, 5. Yeah. So I will not say more here because this is something going. What especially and also with XLZD is also to measure the width at and so on, right? And reach a really low statistical uncertainty on the people. Our energy threshold, I mentioned it here, but our energy threshold is about 1. This flux is where it just hasn't been measured before. Now, in terms of coherent scattering, so the goal was here to observe this process, right? Neutrino coherently scattering on a nucleus, in our case, of course, on the xenon nucleus. Now, the bad news is that, the good news is that you expect lots of events. The bad news is that these are really low energy events. So the majority is below roughly 4 kV nuclear recoil energy, right? So in the plot that I showed before, again, we have here the electronic recoil background. This is where we would expect this WIMP. And this is where we expect the solar boron 8 neutrinos, where you also have this accidental coincidence background. So seeing those neutrinos means that you have to work on techniques to reduce that background. And yeah, I gave a talk about neutrino physics with dark matter detectors at Neutrino in Milano last summer, and I liked Cecilia's talk because she said, you know, these are the kind of measurements that we are doing here are flavor democratic, right? Because of this coherent scattering, you don't care about the flavor. So all flavors will contribute to your event rate. And that's, of course, the same for, for supernova neutrinos. So indeed, we were able to see this flux from boron 8 neutrinos, and I will not be able to go into the detail. You could check out this PRL. So the discovery significance was 2.7 sigma. So we didn't reach 3 sigma, but you know, it's different than, in my opinion, than if you look for dark matter. Obviously, you would not claim an observation or an indication, as we have the title of the paper, if you would be looking for some beyond standard model signal. But the boron 8 neutrinos, we know already that they exist. They have been measured in all flavors by SNON. So this was the first detection of elastic nuclear recoils from astrophysical neutrinos, first measurement on target, and also first step, right? So what you can see here is the flux. So this is the measurement by SNO. More than 10 years ago. Then we did on 1 ton with a search, and we could only set limits on the flux, the same for Panda X in the past. But then this is our determination with XenonnT, and there's also a paper. I don't have it on plot, but there's also a paper actually by Panda X 4 ton. So obviously these errors on the flux are still pretty large, but this is something that we aim to improve. with existing data and then also with future data, right? So we can already reach 5 sigma discovery with data in hand. And this is a plot where you show the flux average as a function of neutron number. So these were this first measurement by coherent. They use these PIDAR sources, so neutrinos that have higher energy. So you have kind of somewhat loss of coherence, right? So they measured it on cesium iodide, then later also on argon and then germanium. And as I mentioned, this is actually with XenonnT was the first measurement on xenon. And because the boron 8 neutrinos have lower, this is a plot redrawn from Kate Scholberg's talk, but this because they have lower energies, you don't have this coherence loss in this case. And now they're actually this plot should be updated because Conus has a first measurement in germanium with reactor. So anyway, we were happy, of course, because this was apparently one of the highlights of the year. So our measurement and also the one from Panda X. And just one slide on the history. So, if you look at the really old papers, this was also long before I started, but the 7-base detectors were first proposed as neutrino observatories in the mid-80s. There's this paper by Drukier and Stodolsky. And then Goodman and Witten picked up, followed up on this and proposed that these detectors can also be used to detect some possible candidates for dark matter, right? This weak scale. And at least to me, it was interesting that it took exactly 40 years until dark matter detectors now actually observed these solar neutrinos via sevens for the first time. Proposed by Drukier and Stodolsky with superconducting grains. These were not, in the end, was not a technology that could be scaled, but with these large liquid xenon detectors. So yeah, just a side note. So I'm coming to the summary and outlook. So the nature of dark matter is still an enigma, almost 100 years challenge, not quite yet. If you start to count with 1933, we have some ways to go. The direct dark matter detection experiments must cover quite a large range in dark matter masses and cross sections. Here I focused mostly on weak scale dark matter. The principal challenges, I would say, is to reduce the energy thresholds even further. That means to probe lower mass dark matter candidates, also to reduce and understand backgrounds with new technologies, especially with the quantum-based technologies. You also have backgrounds and you first must understand their origin. And at the same time, you have to increase the target masses just because we haven't seen any particles yet. So the main goal would be, of course, to discover these new dark species. And in any case, to explore this parameter space until the cosmic neutrinos will start dominating the rates. Matter candidates. We also look for other things, solar axions and so on. And hopefully prepared, or we should for the unexpected. So that would be my goal at latest, by 2033, the PDG should have some new entry with a mass, spin, half-life, lifetime, some cross sections and so on of a new particle. Let's see if that happens. I should say that we plan to start taking data with XLCT by 2031 or so. So so I'll stop here. Thank you. And I take questions.